Hi there. So today I'm going to talk about section 5.2, which is called Exponential and Logarithmic Models. So let us begin. So log and exponential models. All right, so some of this material in this section I've actually alluded to in our previous sections in 5.0 and 5.1, and some of this will be newer material. So what I intend to do is just work through examples and talk about important terminology, and then of course I work examples very similar to what you're going to have to do. All right. Now, again, we know that logarithmic and exponential functions undo each other. Remember, they're inverses of each other. Okay, so we're going to use these very often to solve some applications. But what I would like to do is take a slightly more complicated version of what we were doing in the last section and show you how to solve it, and then we will work with some models. Okay, so again, what I would like to do is just take an example that's a little more complicated, and then we can practice how we would do this. So my first example is, suppose we have 1.7 times 2.1 to the 3x power, and that's equal to 2 times 4.5 to the power of x. Now, let me just tell you one thing. First off, in our previous examples, it was kind of like this is what we would have. Okay? Now, how did we go about solving this? Remember, I mentioned that mantra, isolate your exponential. So the first thing you would do is divide both sides by 1.7, and then you'd have your exponential alone, and you would take the log. Okay? Now, this one is more complicated because now we have exponentials on both sides. So, again, what you want to do is think of that mantra, isolate your exponential, but notice since we have two exponential functions, what we want to do is get all of our exponential functions on one side and all of our constants on the other side. So, let's do that. What I'm going to do is I'm going to move him to the other side by dividing by 4.5 to the power of x. Then I think you'll grant me on my left side I have 1.7, 2.1 to the 3x power over 4.5 to the x power, and that's equal to 2. Now, our left side looks like a wreck, and our right side looks pretty nice. Thing is, again, we want all of our exponentials alone, so we want to get rid of this 1.7. So what I'm going to do now is divide both sides by 1.7. If I do that, then on my left side I have 2.1 to the 3x power over 4.5 to the x power, and on my right hand side I have 2 over 1.7. Okay? Now, we can simplify our right-hand side. If you take 2 divided by 1.7, you're going to get 1.176. Okay? The question is, what do we do on our right-hand side? Well, recall for our properties of exponents, if you have a to the x over b to the x, you can write that as a over b to the x. The only issue that's going on here that makes this one look even worse is the fact that we have a 3x power here and an x power here. However, do you all agree that I can write this as 2.1 cubed to the power of x over 4.5 to the power of x? Okay? All I've done going from this step to this step is on my right-hand side I divided. And on my left-hand side, notice if you have something raised to a power raised to another power, you multiply your exponents. Okay? Now, 2.1 cubed is 9.261 to the x over 4.5 to the x is 1.176. And now I can use this property here. I can say, well, that's 9.261 over 4.5 to the x equals 1.176. Now, if you do this division, you'll see that you have 2.058 to the power of x equals 1.176. A lot of work to finally get to where we were with the problems last time. So, just to recap before we take this to completion, if you have an exponential function where there's exponentials on both sides and numbers on both sides, the first goal is get all your exponentials on one side and your numbers on the other side. You can simplify your numbers. And again, you can, if both of these are to the power of x, you could have just gone straight to here. If not, you're going to want to bring that number in. In this case, we cubed it. We put it over one thing. In other words, we took our numerator over our denominator to the power of x, and then we could simplify it. Okay? All of them will follow those same basic steps. Now, in this case, it doesn't matter whether we take the log log or the natural log. As I mentioned to you guys last time, I'm a natural log type of person usually. But remember, what you want to do is take the log of both sides. Then you use the property that says if you take the log of something raised to a power, you can bring your power down in front. So we're going to have x times the natural log of 2.058 is the natural log of 1.176. And finally, to get x all by its lonesome, you divide both sides by the natural log of 2.058. So you're going to get x to be the natural log of 1.176 over the natural log of 2.058. And in case you really care what that answer is, you will get approximately 0.22. And there we have it. All right. So, some important terminology that you will see is as follows. What I'm going to do is talk to you guys about what the terminology is, and then I'll be sure to work through at least one example. Okay? The first bit of terminology that you're going to see that we have is something called doubling time. Okay? By definition, that is the time it takes for the amount present to double. Okay? And when you're talking about doubling, it's growing 100%. Okay? So let's talk about an example. Suppose I tell you if the population doubles every 10 years, what we want to know is what is its continuous growth rate. Okay, now one thing that this requires you to remember is when we're talking about things growing and growing exponentially, if you see the word continuous growth rate, you know you want to write this with a base of E. Okay? Otherwise, it's annual growth rate or however it is given. All right? So, the formula that I tend to use for all of these word problems when we have a continuous growth rate is I use P equals P sub 0 e to the kt. Okay? Now, why do I use that? Because usually we're talking about populations of some sort. It really doesn't matter what letter you use. The thing you have to keep in mind is that the number in front of your exponential is your initial amount. So that's your initial amount. The K is either your growth or decay rate. And T is given in as however many years. Okay? So let's talk about what we're given and what we're asked for. We want to find the continuous growth rate. So from that, I know in my head I'm looking for K. Okay? Because when we have a continuous growth rate, by definition, that's my value of K. Well, let's see what we know. We know that when T equals 10, my population doubles. So will you guys grant me then, when T equals 10, whatever P sub 0 is, my initial population, when T equals 10, I've got twice that. That's what it means to double. Okay? So let's plug this in and see where it gets us. Again, when I plug in T equals 10, so I have P sub 0 e to the 10K, I know that my population has doubled. So, does this give us enough information to find my value of K? I claim it absolutely does. Okay? You might wonder how, but let me show you. Again, you want to isolate your exponential, so what I'm going to do is divide both sides by P sub 0. If I do that, that cancels it on both sides, and I claim I'm left with 2 is equal to e to the 10K. Now, whenever I have a base of e, I know the way that I'm going to solve for my exponent is natural log. Okay? So I'll take the natural log of both sides, and I claim I get the natural log of 2. On my right-hand side, using the fact that these are inverses, I'm left with 10K. Therefore, K is the natural log of 2 divided by 10. So we can compute that, and we're going to get K to be 0.0693. So my answer would be about 6.93%. All right, if that's funky, don't worry. We've got a lot of examples to do, and you'll see that they all mimic each other in quite a very similar way. All right, now the next piece of important terminology that you're going to see is something called the half-life. Okay, the half-life is the time it takes for the amount to have. Okay? You can think of that as decreasing by a factor of 2. I always just think of it as it's 1/2 of whatever that original amount is. Now, half-life is used very, very frequently when you want to talk about, for example, carbon dating. If somebody's on an archaeological dig and they want to date whatever artifacts they might find, very often what they do is they use the half-life. Okay? So let's do a couple of examples involving the half-life. Let's first find the half-life of a substance if it decays at a continuous rate of 11% per minute. Okay, two things jump right out at me. Number one, it's a continuous decay. Therefore, again, I know that I'm going to use a base of E. The other thing I note is that since it decays at a particular rate, I'm given my value of k, I have to remember that it's going to be negative because it's decay. So the continuous tells me use a base of e. Okay? The fact that it decays at a rate of 11% per minute tells me that my k is negative 0.11. Okay? So, what is it that I'm wanting to do? I'm wanting to find the half-life. Notice the half-life is defined in terms of time. In other words, when you're asked to find the half-life, you're wanting to find t. Okay? So if t is what we're looking for, I better be given some information about p or p sub 0. And in fact, I am. I'm wanting to find my value of t when half of my substance is left. In other words, I'm wanting to find my value of t when I have half of the original amount. Okay? So, we're going to go through and solve this in a very similar manner. Again, isolate your exponential, so we'll divide both sides by p sub 0. Notice I have 1/2 on my left, and I'm left with e to the negative 0.11t. Well, I solve this in exactly the same way. Take the natural log of both sides. I have the natural log of 1/2 on my left. These guys are inverses, so I'm left with negative 0.11t. And to get t all by its lonesome, I divide both sides by negative 0.11. So I'm going to take the natural log of 1/2 divided by negative 0.11, and I'm going to get t to be 6.3. Now, it's a fluke that we got I think it was 9.3 in the last example. They're not all going to have 6s and 3s in them, okay? So, our answer, though, is in 6.3 minutes. Okay? Now, I'd like to do one more half-life question, but this one's going to look a little bit different. Okay? Now what I want us to do, again, is to find the half-life of a substance. But now I'm going to say if it decays at an annual rate of 5.471%. Okay, notice, big difference. That was a continuous growth rate. That told me I have a base of E. This is an annual growth rate, so using the p's, well, we could just say that's times b to the t power. Okay, why did I use this form? Because again, it's not a continuous growth rate, it's an annual growth rate. Now, I claim we can get this value for our base. Okay, remember, if it's an annual growth or decay rate, well, if it's a growth rate, remember you take 1 plus r. If it's a decay rate, you take 1 minus r. So to get this value of b, we're going to take 1 minus 0.05471. Okay? Remember, you change it into decimal form and then take 1 minus that value. So I claim my formula in this example, well, if you do this computation, you get 0.94529 to the power of t. And now this is the formula that we're going to be dealing with. Okay? I just wanted to contrast that continuous versus annual. All right. Now, Again, we're wanting to find the half-life. Remember, half-life is the time. What is it the time for? It's the time it takes to have half of this amount present. In other words, the amount present is going to be 1/2 of the original amount. And I claim from here on out, we can solve this in much the same way. Unfortunately, when you take the log, things don't cancel out quite as nicely, but that's okay. We can deal with that. Okay? Let's take this to completion. Again, the first thing you do is isolate your exponential, divide both sides by the number in front. So we get 1/2 is 0.94529 to the power of t. How do we solve this? Again, we'll take the log of both sides. So I have the natural log of 1/2 is the natural log of 0.94529 to the power of t. My next step is to bring my exponent down in front. So I have the natural log of 1/2 is t times the natural log of 0.94529. To get t all by its lonesome, we'll just divide both sides by this natural log. So I have the natural log of 1/2 over the natural log of 0.94529. And again, not that we really care what the answer is, but we will compute it anyway. You're going to get t to be about 12.32. Okay, and since it's an annual, we'll say years. Okay, so what I want to emphasize again is the distinction between continuous growth and decay versus annual growth and decay. All right, so again, when we have continuous, we have a base of E. When we have an annual, we have a base of A, and remember A is 1 plus or minus R, depending upon whether or not you have growth or decay. Now, our next project in this section is as follows. It turns out that if you have an exponential function written in terms of base E, you can rewrite it into an equivalent form with a base of A. And in a similar manner, if you have an exponential function in the form of base A, you can write it in an equivalent fashion with a base of E. And that's what we're going to talk about right now. Just very quickly how to go back and forth, and then we're just going to play with a few more examples. Okay? So, let's say the following. It turns out that any exponential function can be written in either form. In other words, say Q is A times B to the T, or Q is A e to the KT. So what I would like to do is show you how to go from one direction to the other, and then vice versa, of course. Okay? Now, let's look at these two forms. Notice A is the same, and the T is the same. The only difference is here we have a B, and here we have an e to the k. So the thing that I want you guys to notice is e to the k is precisely b. Okay? So, for example, if I start with an exponential with a base of e, and I want to go to an exponential of the form ab to the t, notice again, e to the k is equivalent to b, so what we need to do to go from e to the kt to b to the t is simply compute e to the k. Okay? Why? Because that is precisely equal to b. Let me show you an example. Alrighty, so my example is, suppose we start with q is 0.3 e to the 0.7 times t. Okay, and we want to write this as a times b to the t. Well, the number in front, a, doesn't change. So we have 0.3. We know we're going to have the t, so all we need to do is compute e to the 0.7. So e to the 0.7 is about 2.01. Okay, something I want you to notice. Notice that this is a number greater than 1, which tells us that there's growth going on. Notice here, my exponent is positive, and that tells us that growth is going on. I know this is a huge base, okay? But notice here, it's growing continuously at a rate of 70%. You're going to have a pretty big base. So when you start with a base of e and want to go just to a base of b, all you do is compute e to the k. All right, now to go the other way, let me show you what you're going to do. In other words, if we start with ab to the t and we want to go to a e to the kt, I think you'll grant me this is what we want to do. Okay? Again, b is still equal to e to the k. But will you guys grant me we have b, we need to find k? How do you get to k here? You take the log of both sides. Natural log of b is natural log of e to the k, which is k. So the moral of the story is if you start with a base of b and you want a base of e, take the natural log of b to get k. So let me take an example of this to show you. All right, suppose I have q is 16.487 to the power of t. Notice I'm starting in this form. What I want to do is write it in the form a e to the kt. Well, the a does not change. The e does not change. We're still going to have a t. The thing is we need that b. Or excuse me, we need that k. All right, notice my b is between 0 and 1. Okay? In the back of my head, I remember when an exponential function is written in this form and my base is between 0 and 1, I know there's decay. So in the back of my head, I'm preparing for a negative value of k. All right, well, how do you get that value of k? All you do is take the natural log of b. So the natural log of 0.487 is about negative 0.72. And that's it. All right. Now what I would like to do is go through about 4 or 5 more examples just to solidify the material in this section. Okay? So, my first example, so that's all the theory that we have in this section. So now again, let's just work through more examples. Now my first example here, what I want to do is I want to find the doubling time. And what I have is the following. Let's say that if, let's say, a bank account grows by 2.7% per year. Okay? The first thing to take notice is this is an annual growth. It is not a continuous growth. Because it's an annual growth, I know that right from the get-go, I am going to write this formula with a base of B, not with a base of E. Okay? I claim my base is 1 plus the percentage that it grows by. In other words, well, we can use P or P sub 0. P equals P sub 0, 1.027 to the power of T. Okay? Again, I got my base just by here. Now, I want to find the doubling time. Remember, the doubling time is the time it takes for the original amount, or any amount really, to double. Okay? In other words, we want to find the time. Therefore, we better be given information about this, and I claim we are. We want to find T precisely when my population has doubled or my bank account has doubled. Okay? Remember, with doubling time, you have a 2. With half-life, you have a 1/2. Again, to solve this, isolate your exponential. We'll divide both sides by P sub 0. Hopefully you see that these steps are following a very similar pattern. So we have 2 equals 1.027 to the power of T. And now what we can do is take the log of both sides. Natural log of 2 is the natural log of 1.027 to the power of T. Bring my exponent down in front. So I claim to get T all by his lonesome. I take the natural log of 2 and I divide both sides by the natural log of 1.027. And in case you care, it's about 26 years. I hope you have a long time. It's going to take 26 years for your bank account to double. Okay, now, in a similar manner, let's do another half-life. What if I want to find the half-life for this? It's called Einsteinium 253. But we're given that it decays at a rate of 3.406% per day. All right, notice it does not say a word about continuous, so we're going to use this, P sub 0, B to the T, okay? If it was a base of E, then we would be given that it's a continuous. So, to find my base, the first thing I note is it's decaying, so I have 1 minus 0.03406. 0.03406. So right now I have my formula to be 0.96594 to the power of T. Notice again, we want to find our half-life. That's our time. It's the time for what? It's the time it takes to have half of our original amount present. We'll solve this again by dividing both sides by P sub 0. And if I do that, I'll see that I get a 1/2. And on my right side, I have 0.96594 to the power of t. How do I solve this? Again, take the log of both sides, natural log of 1/2. Remember, if I take the log of this side, I can bring my exponent down in front. Okay, all I did is take the natural log and bring my exponent in front, and then to get t alone, you again divide by whatever you're multiplying by. So the natural log of 0.5 divided by the natural log of 0.96594. And so we are going to get t to be about, oopsie, 1 second, I forgot to divide. Divided by the natural log of 0.96594. And we get t to be about 20, and this was given in days, so in 20 days. All right. Next, let's do this example. Suppose I tell you that a population grows from 11,000, this pen seems like it's wearing out, to 13,000 in 3 years. We're going to assume the growth is exponential, and what we want to do is we want to find, in part A, we want to find the annual growth rate, and in part B, we want to find the continuous growth rate. All right, now how will we go about this? Well, let's go through this. Let's first do part A, where we want to find the annual growth rate. Okay, that tells us we're going to use this form. Okay, we're going to want to find our value of B. Well, what do we know? We know that we start out with a population of 11,000. And we know that we're going to end up with a population of 13,000. Okay? Now, if we want to find the annual growth rate, we're looking for B when T is 3. Okay? So notice, right, it starts out at 11,000. When t equals 3, it becomes 13,000. How do we solve for this? First thing we do is divide both sides by 11,000. So we have 13 over 11 is b cubed. But we don't want to know b cubed. We want to know what b is. So how do you get to b? You raise both sides to the 1/3 power, i.e. take the cube root. And in case you really care, you're going to get B to be about 1.057. So my formula is 1.057 to the power of t. We didn't answer our growth rate though. And actually, why don't I go, well, no, let's go one more decimal place. Okay? So, what would be my growth rate? Notice I got a number greater than 1, so you just move your decimal point 2 places over, and the annual growth rate is 5.73%. Now, let's do part B. Now we want to find our continuous growth rate. That tells me right away that I know I'm going to have a base of E. Again, my initial population is 11,000. Again, T is equal to 3. And my ending population 3 years later is 13,000. How would we get to our value of K? Again, isolate your exponential. So I'm still going to have 13/11 is e to the 3k. Take the natural log of both sides. So we get the natural log of 13/11 is 3k. So then divide both sides by 3 in order to get k. So let's compute these. Natural log of 13/11 divided by 3. You get k to be about 0.0557. In other words, here my continuous growth rate is about 5.57%. Isn't that cool? Now notice, if my beginning and ending amount is got to be the same within the same period of time, my annual growth rate better be higher than my continuous growth rate because this is compounded more frequently. Okay? So, let us do one more example. Okay, cool. Alrighty. Okay, how about this one? 35. Boy, I have a lot more I'd love to do, but let's take this guy. Suppose I tell you that the half-life of nicotine in the body is 2 hours. And what I want us to do is find the continuous growth rate. Okay, notice continuous. Knee-jerk reaction for me, we got a base of E. Okay? We want to find K ultimately. Okay? How are we going to find K? Well, let's see what we're given. Do you agree that when T is 2, I have half of my original population? Pretty slick, huh? Well, to solve for K, which is what we're wanting, divide both sides by p sub 0. And we're going to get 1/2 is e to the 2k. Take the natural log of both sides. You're left with 2k. So k is the natural log of 1/2 divided by 2. And in case you care what that is, you're going to get k to be about negative 0.35. All right, actually one more quick problem, because this is going to be my first example with a graph. All right, last but not least for this section, what if I give you this graph? This is 150, here is, 100, and here is 50, and let's do this. Here is 4, here is 8, and here is 12. Okay? What I want us to do, just using this graph, is estimate the half-life. Okay? Suppose this is the amount of caffeine after drinking a cup of coffee. Notice you're starting out with 150, say, milligrams of caffeine. Given a graph, how would you find the half-life? Well, by definition, it's the time it takes, we'll put this as hours and this is milligrams, for half of the original substance to be present. Well, what's half of 150? I claim it's 75. So we could say after 4 hours. So what we have here then is after 4 hours, okay, we have half of the original amount present, okay? Now, that gives us at least an estimation of our half-life. If from there I asked you to then find out, okay, so now we have given that the half-life is about 4 hours. What if I want to know, let's find the continuous decay rate. Could we do that? I believe so. Notice we have continuous. Notice we have half of the original amount present when t is 4. Again, divide both sides by p sub 0. And we can certainly find our value of k. Again, the natural log of 1/2 is the natural log of e to the 4k, which is 4k. Divide both sides by 4. So we get the natural log of 0.5 divided by 4. We're going to get k to be about negative 0.17. Alrighty. Now, let me ask one other question following this just to make it that much more amusing, and then I promise you I'll be done with this section. It's just there's so many questions I can ask. It's tempting, or it's hard not to. Okay? What if I ask you this? What if now I want you to find how long it takes for 17% of the original amount to decay. This is about as tricky as it will get. Notice, we have this formula. Ooh, let me change this. I'll change it to an 18 just so that 17 doesn't mess you up with this 17. All right, well, we want to find how long. In other words, we know we're looking for time. How long does it take for 18% of the original amount to decay? All right. Will you guys grant me that if 18% decays, that tells us that 82% of the original amount remains? That's the trick. In other words, we want to find the value of t so that we have 82% of the original amount remaining. All right, again, from here on out, you divide both sides by p sub 0, take the natural log of both sides. you get negative 0.17 t. So the time will be the natural log of 0.82 over negative 0.17. So the natural log of 0.82 divided by negative 0.17, and so you're going to get t is about 1.17, and I don't know if any amount of time was given, but we'll just say hours. All right, so again, the catch is if they tell you a certain amount is decaying, you want to talk about what's left. All right, thank you. That completes 5.2.